Okay,
All right.
welcome. All right. I mean, you can get started.
Okay. Hello, everybody. Today's speaker at Origin seminar is Giulia Roccetti, a PhD student at the European Southern Observatory and at the Meteorological Institute at the Ludwig Maximilian University of Munich. Giulia obtained a bachelor's degree in 2020 from the Sapienza University of Rome and a master's degree in 2022 from the Ludwig Maximilian University of Munich. In her research, she combines meteorological and atmospherical studies with astronomy, modeling, and observations, altogether to investigate Earth as an exoplanet. And one of her projects focused on exomoons orbiting free-floating planets and the presence of liquid water on them. However, today, we will hear about modeling Earthshine observations for future exoplanet reflected light missions. Giulia, the floor is yours.
Thank you so much. It's a great pleasure for me to be here and present my science. So as Domi said, I'm Giulia. I'm a third-year PhD student at ESO. And today I will try to show you the work I've been doing in the first 2 years of my PhD, which all is around basically trying to characterize the Earth as an exoplanet for future reflected light missions. So let me start with some context and why I think it's important to start preparing what the next generation of telescopes, both ground-based. For example, you see here a picture of the ELT under construction in Cerro Armazones in Chile, in the Atacama Desert, but as well, for example, the Habitable World Observatory, so the mission concept by NASA, which is also gonna potentially start observing exoplanetary reflected light. So reflected light is something that people already have tried for exoplanets, but we only got upper limit. So it's still not sure if you ever observed really light reflected from the star and then from the exoplanet atmospheres from our ground base of current space-based missions. However, reflected light observations, when are going to be possible, will open a new window of exoplanet characterization. Because differently from what we can currently do on exoplanet characterizations from transit spectroscopy, for example, we're not going to probe anymore only the upper atmosphere of these exoplanets, but we're actually going to be sensitive on the albedo of the planet itself, which is going to be a combination of surface and atmospheric features, in particular clouds, which are really going to affect what we can learn about these distant exoplanets, moving down until rocky ones. At the same time, with reflected light, we can also learn a lot of information about the energy balance, again, related to the albedo, because if we can know how much light is reflected by the planet, we can start thinking about energy balance, climate, and their potential habitability. So my work is actually related to that, because what I do is try to characterize the Earth as an exoplanet. To do that, I use Earthshine observations. Let me introduce what is Earthshine. So Earthshine is actually the sunlight which gets scattered by molecules in Earth's atmosphere or reflected by the planetary surface. Some of these photons might travel on the darker portion of the visible moon and get reflected back on Earth, where we collect them with our ground-based telescopes. This might sound very complicated, but what we're actually doing in reality is to use the moon as a diffuse mirror, which means we really resemble the way we observe an exoplanet in reflected light, because we're going to lose completely the spatial information of where on the atmosphere or surface of the planets these photons got scattered. So the spectra which we are going to collect is like a single pixel spatially unresolved observation of an exoplanet. Now, why do we do this complicating of studying the reflected light from the Earth coming back from the moon instead of using, for example, satellite observations to really characterize our Earth as an exoplanet? I think I would like to point out for a few specific reasons. First of all, what we can usually do with satellite observations is that we can get local properties of the planet because we have really high spatial resolution observations, but this is very different from what we can normally do for exoplanets, where we usually get spatial and unresolved spectra. We don't have yet the power to really image the planets in many different pixels and get different spectra. So we can only get the disintegrated properties of the planets. And at the same time, most of satellite observations either have low spectral resolution mode, which, for example, is different from what we can get from our ground-based observatories with high spectral resolution, or either satellite observations, for example, have a very small wavelength range coverage because they study only specific properties of the planet, while we want a very extended wavelength coverage to try to understand as many information as possible about our exoplanet. So in this context, Earthshine observations really resemble much more the way we can observe exoplanets with respect to what we can get from satellite observations. In addition to what I mentioned already about Earthshine, as you can imagine, of course, we have a big problem about to distinguish which is really the signal coming from Earthshine, so the light reflected by Earth's atmosphere or surface, and what is then this latent transmission through the Earth atmosphere. Of course, the radial velocity shift due to this signal is going to be very, very small, so it's really hard to disentangle among the two, but actually a very good strategy we can use to try to disentangle between the reflected light and the transmission comes by using polarization. So most of our Earthshine observations were taken using spectropolarimeters. Why is that? So as I will explain in a second, photons usually get polarized in an exoplanet by scattering processes happening in the atmosphere. And by definition, in the latent transmission, we're not going to collect any photons which are going to be scattered, which means that the polarization state of our photons before and after the transmission is going to be the same. So this means in this way, using polarization, we can actually forget about the late transmission. We do not need to correct for telluric lines, but we already get like a validated spectra for Earthshine. At the same time, trying to potentially extend this technique, so spectropolarimetry, to study exoplanets, while very tricky, because of course the contrast is going to be more challenging, at the same time can enhance the contrast between the planet and the star, because we expect most of F, G, K type stars to be almost completely unpolarized, and thus measuring some polarization signal from like a planetary system can tell us a lot of information about the properties of the planet itself. And in general, polarization tells us more properties about the planet than intensity alone. So actually, to try to summarize why and what can cause this polarization on an exoplanet, we can focus, for example, on the atmospheric part. So we can have single scattering processes happening mostly by Rayleigh scattering with molecules. We can strongly polarize our light, but we can also have single scattering processes interacting with cloud droplets, for example. So following the Mie scattering theory, which again can polarize our intensity. At the same time, you can also have surface reflection, which can add a huge contribution to polarization. There is one particular feature which I want to mention, which is called ocean glint. If you look here on the bottom at this image, satellite image of the Earth, you might see that there is this really bright spot over the ocean. This spot is called ocean glint. It is the regions where the photons get reflected perpendicular to the direction of the observer. You can see this is already very bright in intensity, but this appears even brighter in linear polarization because, again, this feature polarizes a lot light. At the same time, of course, we also have other components in our exoplanet atmospheres, which can depolarize the signal through multiple scattering processes. This happens mostly with clouds and aerosols, where like our photons are going to go in very complex paths and doing many multiple scattering before coming out from the top of atmosphere. So this is going to depolarize, as well as some surface reflection features, for example, over deserts or other kind of soils. So we have a huge catalog of these Earthshine observations. We have 55 different observations collected on in a time period over than a decade. And here I'm representing 8 of them, just like to give you an idea of the diversity of these observations we have. So you can see I'm listing here the phase angle alpha. So of course, observing Earthshine in different configurations, we can get different illuminated part of the planets. You can see we can go from a very small phase angle where we almost have the full disk illuminated of the Earth until a pretty big phase angle, like up to 135, which is still feasible to do with Earthshine. And you see there is only a small slice of the illuminated side of the planet. And then we have a lot of configurations in between. And we can also try to get different clouds configuration. Of course, observing in different days, in different periods of the year, you get different cloud properties, which are intrinsic in the variability of the planet itself. But also observing in different moments, you can get different configurations in terms of surface coverage. You can go from an almost ocean planet, where we're observing over the Pacific and we have almost no land, to a configuration where we have really a mixture of land and surface properties. Of course, with like these observations, what we want to do is to model them. So let me first say that all these images you see right here are actually simulated images. So what we basically do is to take the cloud properties from satellite observations of the exact date and time of the observations, as well as surface properties, and we try to put them together to really replicate as well as possible the conditions during the observations. And to do that, we use a Monte Carlo radiate transfer code, which is called MYSTIC. MYSTIC is really powerful because it was developed for like Earth remote sensing studies. So it can include really realistic 3D atmospheres and inhomogeneous clouds and surface properties. And this was already applied to actually model Earthshine observations. You can see here like which was the state of the art so far regarding modeling Earthshine. So in this plot, you can see that there is a black solid line, which actually represents the Earthshine observations corrected for lunar depolarization. So this is basically our ground truth in polarization that we should try to fit with our model for 2 different cases in this plot. And all the other different like colors, solid lines, or the triangles, the dots represent different models of the Earth, assuming different surface properties, different clouds. And as you might see, even if here there are a few models that more or less kind of reproduce the observed data, in this other scenario, for example, the model was really incapable of reproducing neither the absorption lines, for example here, neither the continuum and like the spectral slope of the spectrum. So this was actually the beginning from which I started to investigate what was the problem and which physical mechanisms we were still missing or like not representing completely in a correct way to actually try to fit the Earthshine observations and overall try to understand which are the important features for us to put in our model to really resemble and have a ground truth spectra of the Earth seen as an exoplanet. So this led me to 2 different directions. I will start now with the first one, which is related to surface albedo. So this chapter is going to be called now hyperspectral albedo maps, and I will try to explain to you which is the reasoning behind them and why they're important and why they really made a difference in the spectrum. Okay, let me start to say that, of course, as you can imagine, like surface albedo has a hyperspectral nature. So you can see here in this plot, for example, that if we take a pixel over the desert, we expect like as a function of wavelength, the soil albedo to change with different features. But what most Earth system models, so basically climate models for the Earth, which take into account the full complexity of both the atmosphere and the surface properties and the ocean and so on. What you can see is that most of them use a true broadband approach to actually include the albedo in the simulations, which is represented here. So they usually have a constant value in the visible wavelengths and another constant values to represent the albedo of a single pixel in the near infrared. Of course, this misrepresentation can lead to divergences in the results. And this was investigated for the first time in a paper that came out 1 year ago by Bragier et al. What you see here is actually the radiative forcing, which is generated just by comparing the true broadband albedo approach compared to a hyperspectral nature of the surface albedo. And as you can see, the radiative forcing is pretty significant with mean global radiative forcing of the order 3.5 watts per square meters, but which reaches like regional values up to 30 watts per square meters. So this, of course, has a huge impact on the Earth system model runs, and for example, in climatological patterns, such as surface temperature, precipitation, latent heat distribution. As an example, I can show you how a different like Earth system model runs is going to be affected if we treat or not the hyperspectral nature of the albedo. So what you can see here is that we end up with a very complex and nonlinear pattern of where we get like a overestimation or underestimation of the maximum daily temperature, for example, reaching up to 0.6 Kelvin, which is a lot. Of course, as you might know, the current climate policies, like we're really discussing by 0.1 degrees by 0.1 degrees, and which are the like mitigation patterns we need to employ. So it means that including, for example, the hyperspectral natures of the albedo in simulations is really crucial to get better and better predictions for future climate change on Earth. So this is the general context. Now I want to move on what we did and why it also matters if we want to try to apply these to exoplanets, in particular for reflected light observations. So to actually try to generate a hyperspectral albedo maps dataset for the Earth, which is something that was absolutely not available so far, we started with some satellite observations, in particular from the MODIS data. So MODIS is an instrument on board the NASA satellites, Terra and Aqua, and it basically coverages the Earth every 1.5 days. So we could collect a large data set and large sample of these MODIS data of surface reflectance. But what is really the limitation of MODIS and of most satellites is that it is not offered with a hyperspectral cadence, but it only has 7 spectral bands between the visible and near infrared. Now, what we did starting from this MODIS data is to perform a climatology. So we really wanted to have a continuous coverage, pixel by pixel, about the surface albedo. And to do that, so to eliminate all the empty pixels, which can happen due to, for example, cloud coverage when their satellite is passing and measuring over a certain region, or it can be due by, for example, the solar noon. So for example, at high latitude, you can have that the satellite is passing over that particular pixel of the planet when it's already dark. So it's not going to measure any reflectance of the planet. So to try to eliminate all these missing pixels, we did perform basically a climatological average of a 10-year period. So we took data from 2013 to 2022, and we filled all the missing values. After that, we also collected a huge sample of soils and vegetation spectra with a very good spectral coverage. These spectra actually come from mainly 3 different data sets, which are called Lucas, EcoStress, and ECRA-FISRIC. These different data sets basically collected in situ or laboratory measurement spectra of different soils, vegetations from different countries of the world. And summing them together, we could collect a really vast data set with more than 26,000 spectra coming from 82 different countries. This is really powerful because previous studies, which already tried to assess which is the role of soils, for example, in canopy tree radiate transfer, already understood that having a huge sample of different soils from as many countries as possible can eliminate a lot of biases. So this is what we really try to do here. And here you can see some example spectra. If we focus, for example, on grass and tree, you can see the typical vegetation red edge peak. So around 700 nanometers, you see this steep increase in the reflectivity due to tree or grass. You can see, as expected, that a typical snow or frost spectra are going to be very, very reflected in the visible and then going down in the near infrared. Ocean water is going to be very, very non-reflective, almost constant at all wavelengths and so on. And what we want to do basically is to combine these soils and vegetation reflectivity spectra with the MODIS climatology. How can we do that? Because we really want to extend from the 7 spectral bands from where we have MODIS data, and now is the albedo really behaving as a function of wavelength. As you can imagine, if we want to go pixel by pixel and try to find which is the best combination of these soils and vegetation and how to fit them, we're going to find a lot of degenerate solutions because we have like more than 26,000 spectra. So to actually solve this problem, we applied a principal component analysis algorithm, which means that we selected the most representative eigenvectors, which host the main information about the different types of soils and vegetations, and we applied the eigenvectors to the MODIS climatology. Doing that, we could really create a new dataset, which we called HAMSTER. HAMSTER stands for Hyperspectral Albedo Maps Dataset for High Spatial and Temporal Resolution. So this is really a global dataset about hyperspectral albedo maps with a spectral resolution of 10 nanometers. a very good spatial resolution as well of 0.05 degrees and a temporal resolution of 8 days. This dataset was, of course, also validated against other satellite observations, in particular from gestationary satellites from the Severi and Tropami instrument. So what we have been doing here, for example, is to take 100 instruments which can measure the surface albedo, but at different wavelengths than the particular wavelengths of MODIS. And we were actually able to see how well is our HAMSTER dataset is doing reproducing the surface albedo outside the wavelengths in which it was trained, which are the MODIS wavelengths. And you can see here an example, for example, so we see HAMSTER versus Severi, and you can see that the random mean square error is actually pretty good, and is really like, apart from very, very few pixels, which shows small discrepancies, it is reproducing very well the expected albedo as measured by another satellite instrument. So this really validated our dataset. Now, to show you what it means to really have a spectral coverage of the surface albedo, I created here this movie. So we can see how the albedo is changing as a function of wavelength. If I start this video again, what you can see is that the Earth is gonna get very, very bright here around 700 nanometers due to the vegetation red edge peak. While going to the near infrared, you can see that both Greenland and Antarctica are getting darker and darker. Now also the vegetation red edge is basically switching off. And we can see that in the near infrared, we have this strong, high reflectivity of desert areas. You see very well here the Sahara Desert. You see other desert features. This is really nice and really interesting because this is also what, at the end, we are looking when we try to do exoplanet characterization and try to see which are the wavelengths in which we try to do retrievals of different properties. So to show you also another example of something that is possible now to do with HAMSTER, which I didn't speak about yet, is that we not only have a global coverage of how the surface reflectivity is changing as a function of spatial distribution, but we also have different temporal albedo maps. So we can also see how the surface reflectivity is changing with time during the different seasons. So to show you an example, I'm plotting here, which is the reflectivity, the average reflectivity of the planet during the spring and autumn equinoxes. And you can see that there is a very big jump here in the visible wavelengths. This is actually pretty impressive and really interesting to try to see also if, for example, for an exoplanet, we can measure such a difference in the reflectivity. And this is actually due from the fact that the northern hemisphere, which has basically 80% of the total length of the planet, has a lot of much more snow coverage during March with respect to September. So this is really this peak in reflectivity that you might see here, which is only showing basically during March. This is actually something very cool that was not possible to be obtained before with HAMSTER, and really try to put together both the spatial, temporal, and spectral variability of the albedo. To show some more examples, we also try to compare different regions of the planet. So we selected different forest areas over the globe. Here, for example, I'm showing a comparison between the Amazon rainforest, the African savanna, and subboreal forest over Canada and over Siberia. And what you can see is that the different gray shaded area actually represent the 7 MODIS bands from which HAMSTER was trained. So these gray regions is really where we had the MODIS data, while the continuum green curve is what we actually reconstructed in applying the principal component analysis regression algorithm. What you can also see is that we are trying to see if there are any seasonal variability among the different regions. And as expected, for the Amazon rainforest, we do not see almost any seasonal change. And this is really, again, expected and telling us that HAMSTER is doing well, because for a rainforest, we do not expect any big seasonal variability. Well, you can start to see that we have seasonal patterns happening both over the savanna region I selected or over the boreal forest. Here, for example, in the boreal forest, you can see that we have really a steep increase in the reflectivity during the winter months, the boreal winter, as expected, because these areas are gonna get snow coverage, like total partial snow coverage, which is greatly gonna increase the reflectivity. While when we go back to the summer months, so the dark green, you can see that the overall spectra of the forest resembles very much the one of the Amazon rainforest. I think this is something very cool and very powerful to really try to apply in both for Earth system models and exoplanets. We did something similar for deserts. So here I'm comparing different deserts regions, for example, the Sahara Desert with deserts over Australia, the Atacama Desert or Gobi Desert. As expected, we have no seasonal variability for the Sahara one, while we get some variability over the Gobi Desert, which is the one that gets the longest period of snowfall coverage. We also have some variability in the Atacama Desert, which is inverted because, of course, the snow coverage over some regions of the Atacama Desert are gonna happen in our boreal summer, because, of course, it's in the southern hemisphere. And what is also interesting to notice here, like comparing deserts, is that the albedo is actually, the scale is not the same, and you can see how reflective is the Sahara Desert, reaching up to 0.6 compared to all the other deserts. And also this is telling us that the PCA was actually capable to understand that the Sahara Desert is made by different soil types and different particles compared to the other deserts, because the Sahara, compared to the other regions, has a lot more of sand and is much more reflected, as was picking up by the PCA in hyperspectral albedo maps. As another comparison, we can also look at different ice sheets. For example, comparing Greenland and Antarctica. We start with a very, very high reflectivity of 400 nanometers, and we go down until the near infrared. Here, all the seasonal variability is due to like snow melt and the formation of some lakes over the surface of the glaciers, which are gonna impact the reflectivity of the ice sheets. And for example, a last comparison that we performed is regarding cities. So we really try to see if we could also see which is the typical spectrum of a urban area. So this is not really only the city, but the extended area of Mexico City and Beijing. And you can see that the main spectral features we actually get are the vegetation red edge. So again, we see the steep increase around 700 nanometers, but a very interesting feature we also see is this one around 1.4 microns, which is something really due to concrete. So it's really something we already found in the catalog of spectra we use to train the PCA. So again, this is telling us that with this algorithm and with this approach, we're able to really catch the different surface and coverages of the planet. Okay, so this was the very first step that where we really try to investigate how we can improve the representation of surface albedo to try to match Earthshine observations. But as I mentioned at the beginning, like our reflected light observations are affected not only by surface, but also by clouds. Clouds matter a lot for the reflectivity of the planet. I think this is pretty intuitive. And what I need to investigate it a lot as a second step was how to better treat clouds in our radiative transfer model to really fit the observations. So what's the problem about clouds? I'm showing here two different images. We can start here on the left, and this is a simulated image with our 3D Monte Carlo radiative transfer code, where we put as input for the clouds the Euro 5 reanalysis product. What is a reanalysis product? It's basically a weather forecast model, which is later on improved after the weather event actually happened. So they subsequently take satellite informations and they improve the initial forecast to deliver for example, in this case, hourly data on the atmospheric state of the planet, including all the cloud properties and informations. So taking this Euro 5 reanalysis product for the clouds, as you can see, we are greatly overestimating really the reflectivity of the planet. And clouds appear to be way thicker than they should be. And also the cloud cover appears to be overestimated compared to what we should get. So the work I'm going to show you now is what allowed us, this new approach, to move from this highly reflected planet, which is really not resembling very well the Earth, until something much more realistic as the image on the right. So to do so, what I've been developing is what we call the 3D cloud generator. So the basic idea is that we would like to divide our cloud fields, represented here in the sketch, into subgrids. This is very important because might not be super intuitive, but dividing the clouds in and subpixels, and introducing subgrid horizontal variability is really gonna affect the reflectance of the cloud field and actually is gonna lower it. So this is really what we want to get to really do validation against satellite images and top of atmosphere fluxes. To do that, at the same time, we don't want to change the mass of the clouds and thus their microphysical properties. So we want to conserve the overall grid box optical thickness and as well the cloud cover. We just want to redistribute them in a way that we can lower the reflectance field. This is also actually resembling what is really happening in nature. We don't usually get this like really smeared out cloud properties, but clouds on Earth appear rather patchy, which is actually better represented by like the cloud generator approach. So we introduced this cloud inhomogeneities assigning to the clouds a higher optical thickness, so higher in-cloud optical thickness, but in a way that the total initial grid box optical thickness is going to be conserved. And doing that, we could really get a much better comparison with satellite images. We're still validating that.
Sorry, I think we lost our
And characterization, we really need patchy. They show both subgrid horizontal variability, but also like vertical features and structures, and like really accounting for them is going to be very important to get realistic spectra of the planet. To show here an example, we can also see not only visually from a satellite image, but from, in this case, phase curves. So observing the planet at different phase angles, how much we're going to change the reflectivity of the planet in polarization, both reflectivity and polarization, if we apply the cloud generator approach. So ERA 5 is here the black line, and you can see that even assuming different strategies on how to divide the subgrids for the cloud generator approach, we're actually gonna lower a lot the reflectance of the planet itself, and in polarization, we are gonna greatly increase the polarization, which is gonna be very crucial, and I will show you now for really matching the Earthshine observations catalog. Okay, now trying to put things together and going back to the original problem on like, we have this huge catalog of Earthshine observations, why don't we fit them? What is missing in our model? What shall we do about that? I will try to show you some examples. So first of all, I taking two different scenarios of Earthshine observations. You see, I selected one scenario over an kind of ocean planet. We only see the Pacific Ocean in the illuminated side versus a mixture of ocean and land. I can show you now with the improved clouds and planetary surfaces how well we can match the polarization spectra of Earthshine. So you can see really the difference between simulations and observations, and you can see that we can match very well both the continuum and the spectral features. This is, for example, the oxygen A band, and this is really in good agreement in both cases, for example. For completeness, I'm also showing here what it appears in intensity. As I mentioned at the beginning, unfortunately, Earthshine observations are really hard to be calibrated well for intensity observations. So take them with a grain of salt, but we could still like resemble the main spectral features and spectral characteristics in intensity as well about Earthshine. As a second step, once we have really a validated model, we can also try to see what for potential future like instruments for the extremely large telescopes with, for example, a very high resolution. These are simulations with a resolution of 100,000. We can actually try to see what an Earth-like exoplanet is going to look like. So here I'm simulating the oxygen B band, for example, and I'm showing which is the difference which we can really see between cloudy and cloud-free planets. So you can see how much the different features are going to be affected, not only the continuum, which of course is going to show a very big jump. So we're going to see a very increased reflectivity again for the cloudy planet, while in polarization, this is going to flip, it's going to be the opposite. So for the cloud-free planets, we are going to get much more polarization, while when we had clouds, we're going to introduce a lot of multiple scattering processes in the atmosphere, which is going to lower the linear polarization component of our spectra. But what is very interesting is also the effect that clouds can really gonna show up for the different lines. But probably even more interesting is the role that polarization can have in trying to detect different surface features. So still sticking with these high resolution spectra in intensity, what you can see here is that we have again a cloud-free planet where we put an ocean and a full rocky surface. And as you can see in the spectra, we do see a small shift of the different lines. Of course, we have a lot of lines here. We are really high resolution. And you see there is a small shift. But as soon as you put clouds, so you get a cloudy planet, the shift is basically gone. I can't really distinguish anymore between the two different surfaces. However, this is something that was already found in low resolution by Stam. If we do the same in polarization, the interesting feature is that in polarization, for a cloud-free planet, the ocean continuum is going to be up here, and all the lines of water, so the H2O wide band, are going to be shown in absorption. So are going to lower the continuum, which is up here. While again, for the cloud-free planet, all the water lines over a rocky surface are actually going to show in emission. So the continuum for the rocky planet is down here, and all the lines are actually showing up in emissions compared to the continuum. And even if you put clouds, what you can see is that, of course, you're going to miss this big difference you had without clouds, but the behavior is going to be still exactly the same. So the continuum for the ocean surface planet is going to be up here, and all the lines are going to be in absorption, while the continuum for the cloudy planet with like a continent on as a surface is going to be down here, and all the lines are going to be shown in emission. Actually, from here until in this actually part of the H2O wide band, we can even see that the lines get saturated, so it doesn't matter anymore what do you put as a different surface. All the lines are going to be shown exactly the same and fully saturated. But where you don't saturate the lines, this is very powerful. Polarization is showing that we can actually have a way to actually disentangle among different surface properties for an exoplanet, just looking at the water lines and which is their behavior. So if they are going to go in emissions compared to if they go in absorption. Now, to conclude, I also want to show you how polarization can help us in distinguishing surface variability, this time not looking, for example, at high-resolution spectrographs or spectropolarimeters, which this is something we are going to hope for ground-based instrumentations, but also for space-based. So I'm not going to show you any more spectra, but phase curves. So how the planet is going to be, it's going to show up at different phase angles. You can see here in intensity, we have like two different models. We have again an ocean planet and a rocky planet. And what you can see is that the two models are almost degenerate. There is not a lot of spread among the models. There is only here a little bit of spread, but this is within the cloud variability, because the shaded area I'm representing here is actually the cloud variability of the planet itself. So I just ran the same models with many, many different cloud files, and then took the 1 sigma deviations we can have from the different models. So this is telling us that in intensity, looking at the phase angle, we can't really distinguish at any point almost between the ocean and the rocky scenario. Well, if we look about the same in polarization, what is interesting to see is that from 90 degrees of phase angle on, the two models, which are also pretty degenerate, start to have a very big spread. So if you look at high phase angle in this region from 110 to 150, you can see that the spread among the two models is really large and is much larger than the spread due to the cloud variability. So this is really encouraging, and it's telling us that there is a lot of like detection power about surface properties, only looking at the polarization spectra, which is something complementary, but which cannot be done using intensity alone. We are also overplotting our Earthshine observations that, as I showed you at the beginning, I try to classify between ocean and rocky surfaces. Of course, let's remind that the Earth is never a full ocean or a full like land planet, but also like applying the data over these theoretical findings, we see that this pattern, which is shown by the simulation, is actually pretty much respected also in our observations and the way we classify them. So this is really powerful because this can give us actually a way we can actually try to distinguish among surface properties and surface variability of the planet with like the future generation of telescopes. So to conclude, I would like to recap what I spoke about. So we think that Earthshine is a very nice way we have to characterize the Earth as a spatial unresolved exoplanet in reflected light, and we can actually do that on many different phase angles, try to see which is really the spectral and temporal variability of the Earth studied as an exoplanet, and try to see how we should model that in an optimal way to prepare also for future exoplanet observations. In general, I spoke a lot about polarization. I explained that we have a very strategical reason to use that to calibrate our Earthshine spectra. But at the same time, we also discovered that polarization is really sensitive to the planetary surface and cloud properties of the planet, and has much more diagnostic power than intensity alone, and can actually help us distinguish among different planet scenario and potentially make our retrieval methods less degenerate if also polarization is included. At the same time, I also spoke about the major challenges we had in trying to model and really fit the observations of the Earth as an exoplanet, which came from two components. The representation of land surface albedo, which is hyperspectral, and this is really crucial to include that to get realistic spectra of the planet and a good spectral slope on how we should model the spectrum in both intensity and polarization. So for this reason, we developed HAMSTER, which really is taking into account the spectral, temporal, and spatial variability of land surface albedo for the Earth. And at the same time, I also spoke about clouds and how important it is for us to represent clouds in a correct way and make them patchy and as realistic as possible, because the radiative response is going to affect a lot the way we model and try to compare exoplanet atmosphere observations. Thank you very much. I'm very happy to take questions.
So for online audience, if you have any questions, please do raise your hand. And do we have any questions in the room? Okay, go ahead, Everett.
Really excellent work, excellent presentation. I was just wondering if you saw the effects of volcanic ash after any eruptions, and that shows up in your PCA analysis.
Oh, thanks for the question. That's very interesting. I never focused on that, so I never really tried, but I think this is something interesting to actually try to see if I can get that as well, this feature. Thank you.
So I have a question that's related to the wavelength dependent plot you showed. So you showed the plot that on Earth, if there's no cloud, then the desert area would be most obvious in the infrared wavelength. But what would it look like if we have cloud?
You mean this plot? No, sorry.
Yeah.
Yeah, of course, like all these features, as soon as you had clouds, are going to be smeared out a lot. So I don't expect, of course, that for an exoplanet, we can distinguish of any of these variation about like the albedo, surface albedo of the planet. However, I think the message is that this still matters a lot, in particular, which is the spectral dependence, because this is going to affect the spectral slope of our spectra. So if we just put like a continuous value of albedo of 0.3, we can't really represent well the slope of the spectra for our exoplanets or Earth as an exoplanet.
All right, thank you. Dominica, do you want to ask your question?
Yeah, thank you for the presentation. I really enjoyed it. As you know, I'm an observer, so I have a typical observer question. You mentioned that, well, you described a lot high resolution, possible high resolution parametric observations. So if we wanted to perform these observations, what kind of telescope time are we talking, investment are we talking about? Like, what would be the major challenges to actually to conduct this study?
Yeah, that's an excellent question. This is, of course, really tricky. And so, for example, with current facilities, I have a proposal as a PI for try to observe, like we call this as a proof of concept to try to see if we can detect any polarization for a hot Jupiter planet. We got time from FORCE-2. This is a low resolution spectral polarimeter at the VLT. And we're still in the analysis part of the data. We're trying to see if we detected anything or not. But something you can potentially look for is if, for example, there is an increase in the polarization over blue wavelengths, which is coming from Rayleigh scattering or not. This is the kind of feature that at the moment we can potentially, we don't know yet, detect. So we need larger telescopes, as always, we need better instruments. And like the next very big thing is gonna be the ELT, of course, so the extremely large telescope. Right now, there are no instruments which are planned to have polarization. So the first and second generation instruments, for example, the ANDES spectrograph is not gonna have a spectral polarimetry mode. However, for the PCS, which is the planetary camera spectrograph, which is gonna be a second, third potential instrument for the ELT, they're still like under discussion. This can potentially have a polarization camera, so something similar to what Sphere is doing for the VLT, but of course scaled up for the ELT. This is still under discussion, and the big question is there is really by technology driven if it is possible to actually really get like a relative polarization contrast using like all the different segments from the ELT. But if this is going to be possible, this can open up a lot of avenues, I would say, for characterizing both disks, of course, because we already saw how important was where like sphere polarized images for protoplanetary disks, in particular dust properties and characterization, and this can also open up new avenues, I would say, for exoplanets as well. In particular, because PCS is really going to be designed with all the, let's say, the design is really going to be focusing on like golden cases like rocky exoplanets orbiting, I don't know, Proxima b or like protoplanetary disks. So in principle, this is going to work very well.
All right, thank you. Let's keep fingers crossed for the polarimetry on ELT.
All right, do we have other questions? Yes, go ahead, Everett.
Yeah, I was wondering about the intensity. You showed the intensity and the polarization for the land versus ocean. I was wondering if it looked like there were some angles where the intensity could work, like around 150, or is it just going to be the contrast? You know, trying to measure the contrast where the flux is so low is going to be a challenge.
Yes, like here, you're right. Like the cloud variability is almost zero, so you can see that you can potentially distinguish that. But at the same time, as you already mentioned, we also need to consider that like the contour is gonna be smaller and smaller because we only have here like, I don't know, 20% of the flux we are gonna get really from the planet. But this of course also apply for polarization. So this is why this is also gonna be tricky. But at the same time here, potentially using polarization, we do not need to care about stellar contamination as much because as I try to explain, depending on which star you're gonna pick, but for half GK type stars, we expect them to be almost completely unpolarized, and thus if you collect polarized photons, even if they are like not many photons, because of course the contrast is going to be very low. At the same time, this eliminates you the problem of really correcting for the stellar contamination.
I see. Thanks for explaining.
Follow-up question about this same plot. Do you think that this type of dependence of polarization on phase angle is diagnostic? Like if you were looking at an exoplanet with a, given the correct instrument, et cetera, and you have this curve that has the same shape, would you feel like you could say this is likely to be an ocean world? Or are there, there's a lot of compounding factors, a lot of other things that would be different between an Earth case and an exoplanet. And I'm not sure if any of the surface properties could also contribute to that, or do you think that you could feel fairly confident or no?
Yeah, great question. So I think this is really also in the direction I'm trying to go. So like from really, let's say, Earth as an exoplanet models, try now to expand on a broader parameter space and try to see which other effects are going to appear and how much diagnostic is really in the features we are looking. But for this particular feature, so this like ocean glint thing, I'm fairly confident that it's going to be the same, because even if you try different surface properties, even if you put much more vegetation, you put more deserts, you change the size properties, the grain size of your deserts, whatever you're going to try, let's say, this like really steep increase in polarization is due to this specular reflection over the ocean. And you need a rough surface which is really given only by like an ocean surface with roughness due to wind speed of different sizes, which is going to create the glint. If you don't get that, you can get anything similar to that as an increase in polarization, I would say. So this is not diagnostic in a sense of really knowing which kind of liquid thing you're going to have on your surface, but you can be sure that you have a liquid ocean of something.
Cool.
And last call for questions. If there's no other question, let's thank our speaker again. Thank you, Julie.
Thank you.
Thank you for having me. And nice to meet you all.